going to tape it because I think my video is really blurry. So section 6.4 is different types of differential equations. What's the only way we know how to solve differential equations right now?
Separating variables.
Separating variables, right? We did it once, we did it again. Even when we did the logistic equation, which was like the beast, that was still separating variables. It's just when we have an integral, what do we have to use on the integral to solve it, which was hard for us because we haven't really done it much. Partial fractions, right? But that's not going to happen on the AP exam either. On Todd's it will. Anyway, so what we're going to look at today is another type of differential equation, and then we'll see another type that's related to this closely tomorrow. Okay? So the kind we're going to look at today are called first-order linear differential equations. They're very, very, very common, and there's a couple different ways to solve them. I'm going to show you a way that one of my teachers showed me, which I vastly prefer to the book's weirdo strategy. It comes from stuff you already know, and just thinking about calculus stuff you already know, and not some strange, I don't know where this came from thing, you know what I mean? So the book has a weird way to do this. Anyway, so the form of this kind of equation. This solution technique obviously only works for a certain type of differential equation. It's a very common one though, and you can, it turns out, convert a lot of other differential equations into this if you do like clever algebra. So big time strategy here. Anyway, so the form of this differential equation is this. Doesn't have a complex form really. But if you can get whatever you're working with to fit this form, you can use the strategy that I'm going to show you to solve it, which is not just separating variables. It's a little more involved. Okay, so what do we have going on in this form? Can somebody dissect it for me?
Your differential, y prime is...
Your derivative, y prime, yes.
Plus...
What's over here?
First function.
The function, and isn't that what we're trying to figure out in the end, at the end of the day, is the function y which satisfies this equation? So we're trying to like solve for y here, but in terms of normal stuff like e to the x and x squared and so forth, right? Not in terms of, if we solved it right now for y, what will we have? We'd have a derivative in it still, and it'd still be a differential equation, you know what I mean? We want y, when we're trying to solve a differential equation, we want y in terms of elementary functions that we know the shapes of and that we know the properties of. You know, x squared, y equals x, a line, a parabola, a logarithm, anything that's an elementary function. That's the whole goal whenever you're doing differential equations. Once you have a function, you're solid. I mean, you can do whatever you need with it. You can measure it, you can use it to do all kinds of things, right?
Would you be able to just integrate it how it is right now?
Well, that's a good question, which I'm sure people like Euler and Mr. Isaac Newton tried to do. I mean, this is definitely in their territory. Isaac Newton wouldn't have written it like this. He'd have written it y prime, right? If we integrated it right now, what would happen though?
You have the dy and dx on the same side.
So that would be like become y pretty much, right? And this would be like the integral of some function. This would be the integral of y. But y is in general right now, isn't it? So what's the integral of y when it's in general? I guess it's like y squared over 2. Then we'd have like y and y squared over 2. Could we like solve that explicitly? We could like factor out a y, but it would be tough. But good strategy. It'd be good to try that a little bit on our own maybe, right? So it turns out that none of that's going to work, but there is something that's not too hard that will solve this equation. Before we learn how to solve it though, let's just identify these guys, okay? How do you identify it? So notice, this function only depends on what? X. And this function only depends on
X.
Why do you think they called these P and Q?
Because they're different.
Because they're different. There's no other reason, right? A function depending on x stuck here, and a function depending on x on the other side of the equals. That's the form, okay? So let me give you a couple notes about the form. So I'll try to make this kind of big for the video. First order, because it's first order linear, first order means y prime is the only derivative in there. If there's y double prime or something else like that, y triple prime, deals off. Can't do this. So that kind of limiting, isn't it? But it turns out you can do second order and third order equations really similarly to this. So if you really know this and you take another class, you'll be like, oh, okay, it's not hard. Okay, first order means y prime is the only derivative expression. So don't let that fool you. Like I said, that doesn't mean that you can't easily extend this method to higher orders. It's just technically that's the way it is for us. Okay. What else? We did the first order. What else? Linear. What do you think linear means?
No y squared.
Ah, know what, Paul?
Like y squared.
No y squared. The y term has to be linear. Good, you got it. So linear means, I don't know what I wrote here. The y terms, whatever I wrote, are linear. So like Paul said, no y squareds, no logarithms of y, nothing like that. Once again, you think that's limiting, but this still is a very useful tool.
You only have like one y prime.
I don't know. If you had more than one y prime, could you just smash them together?
That's what I would think.
Okay, so let's start looking at some examples. We've talked enough in general. So
Y
let me just
term
throw
or
some. Adam, yeah? So let me throw some examples up here and we'll decide about them. I don't know if I have enough. I need to try to find some more. Darn it. We'll warm up tomorrow with another couple. I don't know if I can make these up off the top of my head so easily. I haven't seen them for a year. Okay, so the question is, which ones of these fit the first order linear classification and which don't? Does this one look like it fits that classification?
Yep.
Does it need to have an x
Yes or no?
next to the y?
Remember, you can bend it into that if you can.
divide through by x.
If you divide through by x, what happens?
Should work.
This will go
Under that too.
here, and that'll decrease this to, there's a function of x, there's a function of x, y prime. Hey, you've got it, right? So this guy is first order linear. So however we're going to solve that, we could do it on that one. This one, first order linear?
No.
No.
Got a y
Still
double
close.
prime.
This one could be done almost like first order linear, but I don't know. That's not first order. It's second order. It's got a y double prime. Okay, this one.
No.
Paul, you said no, why?
It's got a y squared.
It's got a y squared, dang it. That's not linear. So I'll give you a couple that are tougher to tell tomorrow. I'll try to see if I can cook a couple harder ones up. Pretty easy to identify though, I mean, it's not that bad. Remember, if you can bend it into this form, even if stuff's like on the other side of the equals, see if you can move it into having this form. That's all you need to be able to do. Okay, so let's talk about how we're actually going to do these. Okay, so there's two approaches. The book, and you're welcome to look at this. The book uses this mysterious approach called an integrating factor. I remember when I was tutoring people out at the university and lots of people come in and some of their teachers would teach them this integrating factor way, and I'm like, oh, I don't even understand where this comes from. Using it's not that hard, but it's important that we understand where methods come from too. So I don't like this. I'm going to call my method, not my method, Dr. Lewisell's method, the product rule approach. Because it's something that you guys could reasonably be expected to figure out on your own if I gave you a week. If I gave you guys a week and maybe some subtly little bit of hints here and there, you guys could probably develop this on your own. It would take a lot of effort, a lot of tears, some banging heads, but we would come up with it if we took that one. You know what I mean? So, this is a better approach in my opinion. So here's the idea of the product rule approach. It's like 3 steps, so not long. Here's what you do. First, we're going to multiply by a convenient m. I called it m because I like m and because I'm multiplying by it. You can call it whatever you like. I think that also might match the book's notation, but whatever. Multiply by something convenient. It's like a storage receptacle. Okay? Call it whatever you want. Then we're going to set the derivative of m with respect to x equal to p times m. What p do you think I'm talking about? We seen p today?
Yeah, the first equation multiplied by
Like
y.
p of x, right? The thing multiplied by y. Sweet. So that's what I'm talking about. You'll see it in a second. And then finally, you know what? I don't leave this blank. I want to see if someone can come up with it. So leave 3 blank, but leave a little space there. Okay, let's actually do the problem and see if somebody can tell me what the 3rd step is. The step that's genius. I'm thinking it's possible. It will be worth a candy bar. Full candy bar, your choice.
Turn on.
Did I just see that, Austin?
What did Austin do?
Looked at the notes.
Did you get it? Yeah, I won't say it. I won't say it.
Wow, you just lost your chance.
I know, what is that?
It's okay. It's 2.5.
Okay.
He's not gonna eat it, because if he does, he get too fat. Only I'm allowed.
See, this is why what happened to you last time happened, Chance.
I'm just some bully.
Okay, is this first order linear, first of all?
Yes.
Yes, we've got a y prime. That looks like it's messing things up. What are we going to do, though? Divide by it. So I think that's the first step. Get it into first order linear form. I guess I did put that. If you want to put step 0 on yours, put it into the form. That's fine, right? Anyway, so we're going to divide by x. Get it into that form. I'll try to use some color coding here to help you guys. So we get y prime plus 2 over x times y equals 12x cubed. Now it's definitely in first order linear term. It's a first order linear form. So now step 1 was what? What are we going to do with it?
Multiply by a convenient m.
Multiply by convenient m. What m though? I don't care yet. I'm just going to multiply.
Okay. Sounds good to me.
Okay, then what did I say for step 2? Enlighten me. So I'll try to do m, I guess, all in blue. So over here, like some scratch work, it's kind of like a U sub key, you know what I mean? Like a little scratch work place. So you go dm, dy or dx?
dx.
Yes.
Dx, independent variable, whatever that is. And you set it equal to what?
Derivative of
PM.
p times
What's PM for our problem?
2x.
Okay. Now you're saying, what the heck is this M guy? Where did he come from? Which is understandable. You want to know what M is, right?
It doesn't. I mean,
I would want to know what M is if I was you at this point.
take the derivative.
Isn't this a simple little differential equation you can solve for it?
Where did you get 2x or like
That's because we're setting that PM. That's the weird part. PM, that's where this came from. Anyway, so now we say, hey, we want to know what M is. Let's get it. Is this separable?
Yep.
Yes.
Yes, it is. So we're going to go what? dm divide by
And
m multiply by
dx.
dx, integrate. That's a little mini separable variables problem, isn't it?
Yep.
And then you say, okay, what's this?
Then-
Natural log. And what's this? Oh, let's rewrite it. That's 2x to the negative 1, isn't it?
Oh, yeah. So it's,
Oh! I'm sorry.
yeah. ln of 2x.
It is just,
2
Or 2
ln
ln
of x.
why is it 2 ln of x?
Because you pull that 2 out in front.
Yeah.
He comes out, right? Okay, what are we trying to do here again? We decided we were kind of thinking we want m, right? So we could like see what we actually did over here. That's the idea.
So m equals 2.
Yes.
It.
Yeah.
So we get m equals that stuff. That looks funky though.
Bring the two.
Do we need a plus?
Bring the 2 where, Austin?
To the.
I'm so glad Austin answered this question.
I redeemed myself.
He did. Chop. So what is m? X squared. Do you think we'd have ever guessed this convenient thing ever in the world?
Possibly.
Yes, but it would have taken us a week. That's why I'm saying you'd have taken a while to figure this out on your own, and you guys would have had to work together and come up with stuff, you know what I mean? So now we're going to go back and put it in, and let's see what happens. Shall we?
Well, we just ignore the C.
Ah, yes, I did just ignore the C. Excellent point. So when I integrated on this step, when I'm doing this, I'm kind of just going to ignore the C. So I'm just getting like the generic thing without the C. Good point, Paul. Very good. I'm glad we're still awake. So let's put m back in. I'll try to stay with my colors. So we're going to put x squared y prime, right? And then plus 2 over x squared y equals, what's going to be over here? X squared and x cubed is
X 5.
12x to the 5th.
Technically, that's just.
You're not an algebra student, Adam. Come on. 12x5. It's because you watched that Einstein film, right? And they were like, 2 is for squared.
I don't know.
He was there. I think that's what happened.
What I say in my head. 2x to the 5.
I'm just having fun.
No, that's not allowed.
Okay, so what do we have? Look at that part very carefully and think. Give you a second to ponder. Maybe do some scratch work. That's what I'm looking for. The next step. What is that left-hand side? What is that left-hand side?
Product rule.
What is it?
Product rule.
What do you mean, Paul?
X squared and y prime are the two functions, and
First, the original function plus the
no.
prime plus
X squared
the
and y are the two
derivative
functions.
times the.
It's it's a product rule, isn't it?
Yeah.
Can you kind of see that it's kind of a product rule? The question is, it's a product rule of what?
X squared times y.
So you're telling me this is the derivative of
y x squared.
Is that right? Do a little shorthand calculation over here. If we take the derivative of this, we go first times derivative of second plus second derivative of first. Hey,
Makes
it's
sense.
backwards product rule. We've never seen that before now. Does that make sense? It's like backwards product rule. It's kind of like factoring, isn't it? Kind of similar in terms of concept, but it's a higher level form of that kind of thing. So we can write that down now. And we've got it. So that's the key step. So if you go back in your notes, step 3, you're going to put backwards product rule. So it looks like Paul won the candy bar. So we're going to put backwards product rule. Okay?
Backwards candy.
And why would we want to take that step? Look at this and see if you can solve it. Now it's easy. How do you get rid of a derivative? Remember, what are we trying to do here? What's the goal always in differential equations? Solve for
y.
y. Good. And now we're not going to ignore c this time, so we're going to have yx squared equals 12x to the 6th over 6, right? Plus c. Maybe we should call it a c temp. Yeah, I'm thinking c temp. See if we can absorb something. And then we're going to say, okay, the answer is y equals, we don't have it explicitly, what should we do last? Divide by x squared, right? So we get y equals, that's 2 x to the 6th over x squared is x to the 4th plus, ooh, can I just absorb x squared into that temporary constant?
Prob's not.
Yeah, it's variable on the bottom, right? So I think we'd probably need to write that. So let's just, I guess I called it CT. We could just call it C now, I guess, or whatever. Instead of writing it like that, I want to make it nicer. How else could I write it? Let's go CX.
It's a negative 2.
And I called it CT. I guess I'll stick with it. Okay. There's the solution to that differential equation right there.
Who discovered this?
I don't know. I don't remember. I'm sure it was either a Bernoulli. It's pretty easy. I bet Leibniz discovered this. I got my money on Leibniz, the guy who invented calculus. It's not like they weren't doing any problems after they invented it. This is pretty easy stuff. If you can invent calculus, you can just invent what we just did. You know what I mean? So, should we do one more? Or should we wait till tomorrow? I'm okay either way. I was thinking one more today. Yeah? Let's do one more. Takes a little bit to absorb this. One more, same question. Y prime minus y tangent of t equals 1. Then we'll do the next kind of equation we're going to do which uses this. It's called the Bernoulli equation. So we know who invented that.
Yeah. Multiply through by because it's already in the right frame.
Okay, so let's try to go faster this time because we don't want the video to freak everybody out who's watching it next year or whatever. So, is it in the form?
Yes, it is in the
Yes. First step,
It's multiply by m.
multiply by m. We don't know what m is yet. We now know step 2 is going to find it for us, right? So we're going to say dm d what?
dt.
dt, because that's the independent variable this time, equals,
Y tan t.
you use this part, right?
Oh, tan t of n.
Okay, so I think you need the negative. So technically was negative part of the form? No, so technically p is negative tan t. That's going to be something you got to be careful about, okay? So absorb that negative over here. Negative is part of the p. And I'm supposed to have what else here?
N.
So maybe negative m. Okay. So that's going to be a little bit funny to you, but once you've done it a couple times, it's just reflex. Okay, then you solve. So separate variables. Integrate. That's negative natural log of m. What's the integral of tangent?
Negative cosine of negative. Sorry, negative.
Natural log of
Wow.
cosine, right? Okay. When I e this, what's going to be the problem? Negatives are in the way. Where can we put them?
Can you just get
Well,
rid
you
of
could
it?
just move it down.
Ah! I could get rid of them. Let's see. Did I do that?
Yeah, just multiply through by -4.
Yeah, I did. You could also put them up here, though, right?
You could also,
I'd divide them out.
once you add it as an exponential, you could also flip it because it would be.
Yeah. So you can do lots of ways. I was thinking maybe we had to put them up, but we don't. We can just divide. You guys are right. So then we can go like this. So we get m is cosine. There's the clever choice of m. Now we're going to put it in.
Not fortuitous.
So we're going to say cosine t y prime minus y
Frosty.
tangent t cosine t equals cosine t.
Problems constant.
Right? Okay, what's the next step?
You can't backwards product rule.
Backwards product rule. Now, you can like look at that, and I would encourage you guys, this particular class at least, to try to actually do the product rule in reverse, because that's really good practice trying to make your mind do that. But there is, of course, a simple way you can do this. You can just say d dt. What are you taking the derivative of to get here? What always goes in this blank?
My.
It's always my. Okay? So I would encourage you in your head to try to like do the product rule backwards and at least check it, but it's really always my that's in there. The algorithm always produces my,
Where side did you
which is nice, so it's not hard.
The tangent is like.
Yeah, so this is really what for us, instead of my, what is m?
Cosine.
Cosine of ty. If we took the derivative, what would it be?
That.
First derivative of second
So
plus second, second derivative of first. What's the derivative of cosine? Negative sign. There's the negative. This isn't sine. What's going on?
Oh, you put tangent over, it's sine over cosine, so there's cosines drop out.
Yes, it is. Yeah? Okay. All right. So we've got that. What are we going to do next?
take the integral.
Integrate with respect to what, technically?
dt.
dt, right? That's why these cancel. And you get cosine of ty equals integral of cosine is negative sine, or is it? Positive or negative sine?
Negative.
Derivative of sine is cosine, so it's positive, right? Now watch that, watch that. That's going to get you on a multiple choice in the AP exam. Anyway, last thing, divide by cosine. What's sine over cosine?
What about
Tangent.
You saved us, Austin. Tangent plus,
C over cosine.
so that'd probably be written tangent
Plus secant.
plus secant t constant. And then if they asked you to find a particular solution to this family, would it be any different than what you've done before?
No.
No, you'd plug in, do a tiny bit of algebra, and you'd be done. Okay? So there is first order linear.